everyone, welcome back to How AI is Built. This is Nikolai, I run an AI agency and I am the CTO at a generative AI startup. Today we are back continuing our series on search. Today we have a very special guest. Nils Reimers is one of the researchers who kickstarted the field of dense embeddings, developed sentence transformers, started HuggingFace, no research team, and now leads Cohere's development of search foundational models. We take a look at the evolution of embeddings, the limitations, how they could be overcome in the future, and how you can fix them right now in your applications. Let's do it.
Quite a long time ago, when BERT came out, colleagues of mine have been working on argument mining. So basically finding arguments online on topics. Should we, ban nuclear energy or not? What's the pros and cons to go vegan, stuff like that. And they were quite interested to cluster it. So what are like arguments that are like the same, or what are arguments that are different, so that you can create a mind map and say, okay, this is like nuclear energy, these are all the pros and con arguments. And for the con arguments, we see these 5 big clusters. And in these clusters, we see subclusters. And so we've been using a BERT model, a pairwise classification model in BERT. Say, hey, here's 2 text. Is it the same argument or not? Which works quite well, but has this scalability issue. So if you have 1,000 arguments and you compare 1,000 arguments against another 1,000 arguments, you end up with 1 million combinations. And so I was looking for a more efficient way where embeddings came in to say, okay, you represent these sentences, these arguments as embeddings, and then you run normal clustering on it. And so I was curious, how can you use BERT, which was really novel at that time, to create good text representations so that you can cluster them? And that's how I got into embeddings, mostly first starting on like semantic textual similarities, like how similar are 2 sentences, how similar are 2 arguments. And then over time going into like semantic search, given a query, given a question, how can you find the relevant answer?
What were the main steps along the way, like in the evolution of embeddings? What are the key innovations that brought us to today?
When I started in 2018, there was like very little information and literature on it. So we had from Google, the universal sentence encoder, but the paper didn't have like basically any information. Let's just say, hey, yeah, we're using some architecture and we got a lot of data from the web and it's working good. And there was also like no code available for inference, no code for training. InfraSend from Facebook was available. Sadly, no code for training, but the paper was more informative, where they have been showing how to train on natural language inference data, NLI data. And so I basically recreated InfraSend training pipeline using BERT model and open source it as sentence transformers. And so I think that's like a key part in the field, to like the first code to show how to train good state-of-the-art text embedding models. Another innovation which became popular is constructive learning. So InfraSend, which was state-of-the-art in 2017-18, did like a classification head. So say I take 2 sentences, does it entail, is it neutral, or does it contradict? But constructive training is a lot better, where you say, okay, here's a positive pair, you want to have this close in the vector space, and here's a negative pair, you want to have it distant in the vector space. This is also known as like triplet loss, but that's like mostly on triplets. And then people found ways, and also Google, mainly researchers at Google, found ways to reuse in-batch negatives, where you say, okay, I have my positive pairs and I use all the other data pairs in the batch as a negative. And then people showed, for example, from the Rocket QA people, that you can scale the batch size. So the bigger the batch size, the better the model gets as it sees more and more negatives. And then also, I think the Rocket QA author showed that hard negatives play a big role. So you go from the question and the answer, and then do a big batch to a triplet structure, question, an answer, and a hard negative. And if you have like good, clean hard negatives, you get like a nice boost. And that's also what we see today, that you train mostly on these triplet question, answer, and a good negative. And then you scale up the batch size to a lot of GPUs, different gradient caching mechanisms. And then, from that, you get quite a good text embedding model.
Yeah. What is like the range of different ways with which I can produce an embedding?
Yeah, most use an encoder only model. Some try a decoder only model, but typically encoder only model works better. So you get text in, you get these contextualized word embeddings out. From that, you don't have that many combinations, so you can combine these contextualized word embeddings. You can either take the CLS token, the first token in the text. Some people use the last token in the text with like decoder models, or you use the mean over all the token embeddings. So it's not really that much of a difference how you create them. What's interesting is how they have been trained, what's the data, and what's in the data. What do you consider as similar or not? And what people consider as similar can be very different. So in early works like Laser and LABSE, people have been using embedding models to find translated text. So you have a sentence in English and a sentence in German, and you want to have these translated text close in the vector space. They have been using machine translated text to say, okay, if it's the same text, should be close in the vector space. If it's different text, should be distant. This works really good if you want to find like these bitext pairs, a text in English and a text in another language, but doesn't work well in semantic search. And so it's a bit on your use case. What's your use case? Do you want to do semantic search or classification or clustering or bitext mining or deduplication? And then depending on that, you need to change the mix of your data.
And if I decide to basically train my own embedding model, you basically, like back in the day, I remember training models on a specific task like classification, and then using the intermediate representation of one of the last layers as an embedding as well. Is this still done, or would you still recommend it, or would you just go with an existing embedding model out of the box and basically train it on a set of like similar or not similar examples?
Yeah, totally take a model, existing model, and start from that. If you look at these state-of-the-art models, so much different systems played a role to create these. So it's not really, if you take all the newest models, it's not like that people started from scratch and fine-tune it. It's not even that they took like a base model, like a BERT model and fine-tune it, but it's like a massive spider webs of what people did with pre-training, intermediate training, like middle training, fine-tuning, hard negative mining, hard negative cleaning. So probably if you really want to recreate it from scratch, you need to implement 20 different papers and models and merge it all together. That's a tough one. But yeah, if you want to fine-tune your own model, take a strong model and fine-tune it on the pairs you have and make sure you have the right good data pairs.
How would you actually go about, if you imagine yourself you have a specific task, how would you go about picking an embedding model for that?
It depends a bit on the task. So if your task is mostly, let's say, QA, question answering, semantic search, you have a short question and want to search and answer, there's different leaderboards available. You always have to be careful of the leaderboards. The newest models, they heavily overfitted on them by training on the data in the leaderboards. But this, just pick any of the good models, popular models. Typically, you don't see that much difference between the models. So if you take the newest, hottest model or a model from a year ago or 2 years ago, not that much difference in quality. It becomes more interesting if your task is a bit different than usual. Let's say you want to do like bitext mining, or you want to do cross-lingual classification where you have training data in English, but want to classify in other languages. There, it's mostly try and error. So, or clustering, it's also the same. What we see with clustering, you test five different models, and then you pick whatever you feels the best to you. Because clustering is like a very underspecified task. For example, let's say you have two news headlines, both address, I don't know, let's say Taylor Swift releases a new album, and Taylor Swift goes on world tour, and the other is, I don't know, Ed Sheeran releases new album. Do you want to first cluster on the person? Taylor Swift and Taylor Swift should be on the same album, or do you want to cluster on the what happened, like releasing a new album? And then you want to cluster Taylor Swift and Ed Sheeran releasing a new album. And it's underspecified. There's no correct or incorrect answer. So some people say, hey, they prefer the person over the action. So they say first cluster all the persons together and then the actions. And others say, no, we care about more the action. Don't care so much about the person. And because you have these ambiguity in people and preferences and your task, there's no way how you can say, okay, the one model is better than the other, because some models say first cluster on the person and then on the action, and others first cluster on the action and then on the person. And then it's up to you whatever you like more.
How big would a fine-tuning dataset have to be to make a dent in the model so I can adjust it to have the clustering I would like to have?
Yeah, the challenge is, can people state what's their preference on clustering? In my experience, I had several projects on this. Typically, people are not really good and able to tell how should the clustering happening. Where they say, okay, when should we cluster on the person name? When should we cluster on the action, on the geographical location, on the sentiment or so? So that's the biggest challenge. But yeah, if you can define it and it's not too complex, it works quite well. So we did it with setfit, which is your data efficient fine-tuning methods for classification. You can imagine like classification is like clustering was like limited number of classes. And there we see if you can provide like 10, 20 examples per class, it works well. With clustering, it's a bit more challenging because you have these ambiguity. How many clusters do you want to have? Is it really just 10 clusters you have, or is it a million clusters you want to have, or 10 millions? Is it open-ended? But yeah, for classification, we see 10 examples per class works quite well.
Yeah. And before we touch a little bit into the main part, so what do you think are the main limitations of text embeddings you're currently facing?
Yes, so what we know since, or what we showed in the BERT paper in, I think, 2020 or 22, and also a lot of other researchers showed text embedding models are very terrible out of domain. So they're good on the data you train it on, but then if you use it on some other data, they perform very badly. So what we saw, for example, in the benchmark in BEER, if you train it on Wikipedia, it works really good on semantic search for Wikipedia. But then if you use it on, let's say, community forums like Stack Exchange, or on web data, or on news data, or on scientific papers, it works way worse than lexical search. And so this is like a massive limitation of embeddings. They work on the domains they have been trained for, but they don't work out of domain. And that's like an issue we also currently see with like the newest models on MTab. All the leading models have been trained on the benchmark, some like the test set. So it's not really informative which models are good out of domain. So you always want to look at out of domain performance, never on like in domain performance. So you always want to check, is an embedding model which has been not trained for my task good for the task? And yeah, this is like a massive limitation for embedding models. They work well for what they have been trained for, but we always want to use them in a situation which it has not been trained for. Like most users don't have like training data and can create training data. And so this is interesting to study, like why do have embedding models this massive drop? It's understandable to have this massive drop. So we see the question, then we ask what's the capital of the United States? And then the model knows, yeah, the answer to it is like Washington, D.C. So it's projecting it already to Washington, D.C. So it knows the answer and then projects the embedding in the right space. But if you ask something like long tail, what is, I don't know, this person X known for? And if it has not seen this person before, it's not knowing, okay, is this person an actor? Is it a singer? Is it, I don't know, game developer? Is it an investor? Is it an entrepreneur? And then it's like really hard to find the right spot in the vector space at query time. And so it's you see a massive drop in quality of embeddings when they applied out of domain, applied on your domain, on your language, on named entities that are new, which the model has not been trained for, if it has been used in your enterprise, because you just have like at query time, like I have this question, I need to know the answer to point to the right location. But if I don't know the answer, it's like very hard to point to the right location.
I've seen a paper in LLMs, which was a fine-tuning method, a parameter-efficient one, an alternative to LoRa, which basically added a matrix before the linear layers to basically do a linear transformation, like a projection in another space. Is this like a way you could adapt embeddings as well? Use a pre-existing embedding model, but only train the projection metrics to project it basically into another space?
Yeah, we did some tests on it, learn new words projected, but it comes down again to challenge how do you learn what's new. And it's embeddings are very bad on like long tail. If I type in Nikolai Geralds in my embedding, I assume you're still not that well known as like a Mark Zuckerberg. So if I search for Mark Zuckerberg, it knows, yeah, Mark Zuckerberg, founder of Facebook. But if you search for a different person, which is not like all over the place in your training data, it's very hard to say, okay, what is Nikolai Geralds known for? Is it a podcaster or an actor or an NFL player or, I don't know, a character in a Netflix movie? And so it's hard for the models. So when I search for it and I search for the name Nikolai Geralds, it needs to know, yeah, this person is known for. And yeah, it's a tough one. It's also when you change it, like embedding models, let's say you change your data and you say, okay, Mark Zuckerberg is not connected to Facebook, but Mark Zuckerberg is, I don't know, some fictional character in a game. It's not able to make the transfer. So when you search for Mark Zuckerberg, it tries to find it like in Facebook, but not tries to find it like internally. Let's say you have a system internally, some server, which you mentioned, like Mark Zuckerberg, which is sending some alerts. And then internally you search, hey, what's Mark Zuckerberg doing in our company? It tries to find it in Facebook and not like your crazy system you named Mark Zuckerberg.
Yeah. What are the different methods you have explored to basically adapting embedding models to new domains, and which one is the one that worked best?
Yes, we published also in BERT paper. We started to work on this called was GenQ, generating queries, and then later we published a paper on GPL, generative pseudo labeling. So idea is you go over your corpus, you take a generative model and look at the corpus and say, hey, here's a document, write me a query out of this. And then you use a teacher model to score it. So a cross-encoder model to create a relevance score between the query and the document. And then you train your model on it. That you say, okay, here's a query, here's a positive pair. So you adapt your embedding models on this. And the benefit here is, let's say Mark Zuckerberg has, in your enterprise context, a very different meaning. Let's say Mark Zuckerberg is your, I don't know, quality assurance system, your CI pipeline. And then if you go over your data, you get stuff like, hey, what is Mark Zuckerberg? How can I SSH into Mark Zuckerberg? How do I change Mark Zuckerberg? How do I kill and abort Mark Zuckerberg? So the model learns, hey, it's no longer connected to Facebook, founder of Facebook, but it's connected to your CI pipeline. And then it updates the internal representation.
Yeah.
So,
Is there also a more targeted way? Because in LLMs, there is some research already happening basically for removing information from the model. Is this already happening in embeddings as well?
On removing, I don't know. So totally, I think there's no such thing. Because with generative models, you want to remove like personal information if it has memorized your private phone number. You don't want that the model is like producing your private phone number when someone asks for. But in embeddings, because you produce an embedding, it's not such a big issue. So I haven't seen work on this. We try to induce it on a word level, but then it becomes like a hard task. Like, how do you, let's say in your enterprise data, Mark Zuckerberg, how do you know that Mark Zuckerberg has a different meaning in your context than on the general web? And how do you induce the new meaning? So we were able to do it manually, where we say, hey, Mark Zuckerberg is now our CI pipeline. And then we could see that the model is like able to reason on this. But we haven't found a way to automatically say, hey, these are terms and concepts on your data collection that has a different meaning than on the general web. And this is how to update it. So manually it works, but automatically I haven't seen it working yet.
So we're basically trying to override instead of replace information.
Yeah, we try to override. And yeah, so far, fully fine-tuned, you create a lot of data, fully fine-tuned, and then you hope that it learns. It's again a challenge because if you adapt your model to your enterprise data, it works for this snapshot. But then maybe you get like your data is changing. Let's say you introduce like a new system, Jeff Bezos, which might be your, I don't know, automatic bug report system. And then you would need to overwrite this information again. And so it would mean you need to recreate training data, train your model again. When you train your model again, you need to re-embed all the data you have. And then with the new embeddings, you have to index all the new data you have, which is like very tedious and practical in a large scale, in a non-academic scale or setting. So what would be the dream is like these continuous fine-tuning where you see, hey, there's something new. Now there's a Jeff Bezos system that's doing bug reports, bug summaries. Update this information, update all the embeddings I had connected to Jeff Bezos, and update them also to the new meaning.
We already talked a little bit about it, like the different levels of embedding at the end, like word embeddings, sentence embeddings, or now the universal embeddings, where you basically can put in context of any size or up to a certain limit. What are the limitations of current embeddings, especially for long documents?
Yes. Sadly, it's a bit of a snake oil. These long context embedding models, I've tested basically all of them, not really working well. So it's something between 500 and 1,000 tokens. And then you see, at the best, they're not improving. In many cases, they degrade in quality, some very heavily, like 20 points. So that's, again, be careful what you trust. Because all the benchmarks we have is like on short documents. Let's say MS Mark was like 50 tokens, the documents on average. And so you can really say, hey, yeah, it's working on 50 tokens, and technically my model can support 8,000 tokens. You can't kind of make the conclusion there. The other big limitation is like how much information can you squeeze in a model. Like an embedding, when it has 1,000 dimension, that's 1,000 times 4 bytes, like 4,000 bytes of information you can at max compress into this embedding. It doesn't work that you encode, let's say, 1,000,000 characters or 1,000,000 words in like 4,000 bytes. You will lose information, and you will lose specific information. So the embedding is like a high level gist of your text. So it says, let's say if we take a Wikipedia article about Barack Obama and create an embedding out of the full article, it's a gist, say, hey, this is a Wikipedia article about Barack Obama, his life, his political career, and about him as a person. But it will not capture fine details like when did, I don't know, Barack Obama get engaged and married, when were his kids born. But if you search for it and say, hey, when were like the kids from Barack Obama born, you want to know, okay, is this in the Barack Obama article or Michelle Obama article, or I don't know what's the name of his kids, or like the articles of the kids. So you want to have these zoom in precise information.
Yeah. So I could expect basically that long documents or the embeddings of long documents are better when I have less information dense documents, like for example, legal contracts, which often have so much boilerplate. So I could expect them to probably work better at them as opposed to something like a Wikipedia article, which contains a lot of information at one time.
Yeah, if the model is trained for it, like if it's trained on like legal text, that it filters out this boilerplate, it could. But out of the box, the models have not been really trained on this. Typically, you do like an average of all the words. So you say all the text is like equally relevant. So it focus also puts the boilerplate equally into the embedding. With fine tuning, you could do it. So if you have very good data, very good queries, the model could learn to ignore this boilerplate specifically for your domain. But out of the box, it's hard to say, okay, what's boilerplate, what should you ignore, and what's not boilerplate, and what should you include?
Do you see anything on the horizon beyond chunking or creating a representation of the document like a summary that could help with handling long documents?
What we have is like these re-ranking approaches that works very well also for long documents. So I would say you structure your pipeline in two stages. First stage, you go from 1 million documents to top 100 using lexical search or embeddings. And there it's not necessarily that critical if the relevant document is on position 1 or 5 or 15 or 50. And then in the second stage, in the re-ranking stage, you go over your query, your 100 documents, and they are able to handle long documents. So they can zoom in. So if you ask, hey, when were like the children of Barack Obama born? You say, yeah, I gonna throw in some documents, the Wikipedia article about Obama, the Wikipedia article about Michelle Obama, and so on. And then you hope that the second stage, the zoom in, can zoom in and find the right document.
Do you have any preferred way of basically debugging embeddings, like any visualizations, anything interactive?
Debugging, yeah, I stopped trying to do that. So I see deep learning systems as a black box where when it's not working, it's likely some issue with the data. But you have been trained on so much data that it's hard to say this is like the one data point that's causing it. But just register the issue and try to fix it with data in the next one. So if you see that it's, I don't know, not able to differentiate between boilerplate and non-boilerplate, fix it by adding data to the mix that differentiates between boilerplate and non-boilerplate.
Yeah, and on the like adding data to it, do you have anything additional? Like we talked about it a little bit, like adding additional information or nuances to the embeddings, like the relevance, like how trusted is the source?
Yeah.
What is the most interesting or the best way you have seen so far to do this?
Yeah,
And do you have any ideas where this might go?
that's another challenge on embeddings for search. Stuff like recency is relevant. So if I use embeddings, I search over news articles and ask like how much revenue is Google making. I get a news article from 2009 reporting about the 2009 revenue of Google, which is semantically maybe correct, but I'm probably not that interested in like how much revenue did Google do in 2009. And then other aspects like trustworthiness. Let's say you search over a lot of like news articles, which numbers can you trust? Especially if you go on like social media and you ask, hey, how much revenue is Google making? Is a tweet from 2004 stating Google makes $500 in revenue. Is it trustworthy or not? We would say, yeah, it's not trustworthy. Find the Wall Street Journal from last week reporting about the earnings of Google. I think you can't fix this in embeddings. So the embedding space is not suitable for that. And then typically what we see is this goes again in a re-ranking phase where people typically define like different matrices or axis dimensions which are relevant for them to say, okay, cosine similarity, semantic match is just one. And then you have like recency as a second, trustworthiness, which you somehow measure with PageRank. Is it an official domain or some classifier, or having experts annotated, or in scientific papers, how often is the paper cited, how credible is the author, and have it as the third one. Maybe adding popularity to it, how popular is the site from click logs, click streams, interactions. And then you do a weighting. You say, okay, cosine similarity gets some weight, recency gets some weight, trustworthiness gets some weight, popularity gets some weight. And then you play around with these 4 weights until you get a combination which you're happy with.
Yeah. Do you see any other NLP or more old school ML techniques that seem to work very well with embedding? So, for example, I just for fun on the weekend did XGBoost classifier on embeddings.
Yeah, it's surprisingly strong baseline to take embeddings. Let's say for classification, you take out of the box frozen embeddings, and then you train on top support vector machine or logistic regression classifier. It's way faster to train than do a fully fine-tuning. It's often more robust, especially out of domain. And cross languages. So if you do cross-lingual classification, you just have training data in English, but want to use it in 100 languages. It's very strong. And yeah, Huawei is a company who's using it internally a lot. So they take different embedding models, like 3-4 different embedding models, trained with very different objectives, pass the text through, concatenates the text embeddings, and then train simple logistic regression classifiers on top.
Yeah. Are there any other promising research direction at the moment that you're particularly excited about?
There's so many research directions. The field narrowed down a lot on like dense embeddings, where we see like the biggest support in it. But if we look at the research community, people have been working on sparse embeddings like Splate. People have been working on late interaction models like Cohere, combinations where you combine sparse with dense embeddings, or convert multi-vector to a high-dimensional single vector. It's always a very tough call what works in the end, because yes, you can show it on some academic benchmarks, but then if you go in production, you have a bit different requirements, which can make it challenging, like data is changing, like new data is added, data is deleted. You need to scale to larger quantities. Not all the data is known beforehand, so maybe you start with 1,000 documents, but after you're at 1 billion documents. You have challenges like multi-tenancy, where you say, okay, you have like many different inboxes, which you may need to search individually over. And here we see that some systems fail on it. So there are like some approaches which work really good if your data set is fixed and you say, okay, that's like the 10 million documents I care about and I want to search over. And then they can build like a really good system, but they fail as soon as you want to delete like one document. So if you want to delete one document, you need to rebuild the whole index and the whole architecture, which makes it like impractical in practice. And so it's interesting to observe what works, what doesn't work, what could be made work, like sparse embeddings, for example. In the beginning, where we saw that they are terrible slow with existing search infrastructure like Elasticsearch, you have like query latency times of 5 seconds in it. But then you see innovation on the index structures, that you get like better sparse index structures, who are pushing latencies down and make it feasible in terms of serving. And then it can become like an interesting alternative that can work. But yeah, you always need these both like a good model and good infrastructure, good vector DB supporting these.
What is something you would love to see built in embeddings or in LLMs?
Yeah, long time what I've been pushing and also with some pet project like binary vector DB or the disk vector index. So far, I find vector search in many cases quite expensive, prohibitively expensive. So if you have 1 million documents, it's okay. But if you go to 1 billion, 10 billion, it becomes very expensive as everything is like in memory. It's very slow. I don't know if you want to index 1 billion documents in any of the vector databases. You have to keep the server running for months or so. And yeah, this is like what I've been working a lot. Like, how can you combine different technologies? How can you offload things to disk? What are alternative vector indices? So I think that's an interesting, or I find it interesting. How can you scale to it? We also see it with customers we mostly focus on large customers who then say, yeah, we have, I don't know, 10 petabytes of data, which we want to embed. And then you start thinking, okay, what's a way to do this? Is the model efficient enough? Do you get the throughput? Do you have the index structure? And how can you really search on that?
If people want to start implementing the things we just talked about, where would you point them? Where should they start?
Um, yeah, I think that the face labor library is a hidden gem in our field. The getting started with face is not the easiest, but it has a lot of deep and really cool technologies of different vector compressions, additive vector quantizations, different index structures from IVF to HNSW to hash maps. And you can build very crazy stuff on it. So they have these face index factory, and then you have these very long strings where you run OPQ and then PQ on the Sandroids and an IVF and add HNSW to your Sandroids. And then you have the clusters quantized with additive APQ, stuff like that. And then you get these very long index definition, which no one understands. It's a bit of a problem with face, like no one understands it, and most people are like new to vector search. So it's not really beginner friendly. But once you're in it, you can build these very cool, crazy pipelines. So right now we're working on indexing FineWeb Edu, which is a trillion tokens. It's terabytes of data. But we make it work that you can search with 100 megabytes of memory on it. So you can run it, could run it on your phone and then search the web on it. And if you do it in a normal vector DB, I think I calculated you would need 4 terabytes of memory. So my computer doesn't have 4 terabytes of memory. If you go on a cloud storage, cloud compute, you can get it, but it costs you $50,000 a month if you want to search over FineWeb Edu. And now it's, yeah, you can just break it down, distill it down to work with 100 megabytes of memory so that you can run it on your personal computer and search over it. It's quite good quality.
Crazy. And if people want to follow along with you, where can they do that?
Yeah, I'm Twitter, mostly on Twitter. So any interesting stuff, just search me on Twitter. And yes, there's like different repositories, different projects, blog posts are coming in this direction.
So, what are the practical takeaways? I think, first of all, what kind of surprised me is his view of deep learning as a black box, that he wants to fix the data rather than doing this whole I'm iterating on the model part. And I think this is what I'm seeing more and more, especially with people who are working with or on foundational models, that we are so path dependent already. The amount of work which went into most models would be just impractical to replicate for most companies, if not all, that you don't really want to deviate from any of the existing models, because it would mean that you have to redo a lot of the work, which is often, like he mentioned, a bunch of research papers in sequence on your own and with your own data, which would be just prohibitively expensive and also time intensive. So you're rather trying to fix the data than adjusting the model itself. What was also interesting, the limitations he mentioned, is like, for one, that embeddings only work in domain, and that long context so far doesn't work well. I think these were two of the main ones, and also that people just suck at saying what's similar and what's not. Let's take the first one, like embeddings only work in domain. This points like to the importance of first having your own evaluation data set, which evaluates the different embedding models on your task, on your domain, and especially on your retrieval problem that you're facing with actual customer queries, and labeled documents which are relevant and which are basically irrelevant, like the negatives and positives, and which also points in the direction that you actually need to fine tune or adapt the embeddings to your domain. Whether that's a projection or a fine tune of the embedding model is to be left open, but you really should be careful when you use embedding models out of the box, because you can't really know for certain what is thought of as similar in their implementation. And this leads, I think, directly to the next point, which is like, people suck at saying what is similar and what is not. It's very hard to explicitly state why two sentences and are similar, and it gets even harder as you move up in scale. So when you move to paragraphs, to documents, it gets even harder. This means that RAG as well suffers from the search problem, that it's very cross-functional, it's very cross-domain. You have to collaborate with a lot of people, you have to get customer data, but you have also talked to the experts. So you have to collect different types of feedback. And I think this is the evaluation cycles we also see a lot of with LLMs. You first basically do vibe checks if you implement something new, where you basically, you yourself, the engineer, are the one who is doing the evaluation. Next, you move on to probably a little bit more formal tests, and this often is in the form of experts. If you have them in-house in your company you're working at, that the experts are basically evaluating the results, whether they're relevant or not, or you're actually doing it with test customers or people who are like your customers in your enterprise, and they should basically be chosen by whatever is cheaper for you and your company. When you have the experts in-house and they have the time, take them. If you have good access to customers, or you can test it cheaply in a test environment or test version, use the real customers. And you basically collect more evidence for the different implementations or interventions you're taking in the search application. Also, what was pretty interesting is that his take on long context embeddings, that they just don't work yet, and he's not sure whether they will ever work because of the limited amount of information we can in the end compress into embeddings. And if we take long documents, so much of the information will be just lost. One more interesting part, I think, is the using multiple embeddings and running a classifier on top of it. This is something I haven't seen a lot of, to be honest. And I think he mentioned Huawei is doing this a lot internally, that they are taking different embedding models and concatenating them and then training a classifier on top. and this works more robustly than many of the other classifiers, and especially like BERT-based classifiers, where you add a few layers on top, which are basically the classification head. And I think this is something that's very interesting, actually, integrating more old school techniques, which are very well established, very robust, and very fast, on top of these dense embeddings. So you get a little bit more of the best of both worlds, and you actually can get away from always choosing like a very complex tool for maybe a simple solution. Yes, this is it. This episode basically kickstarts our series on embeddings. We have a bunch of episodes. So, for example, we will be talking to Jo Bergum from Vespa on especially Colpali. We will be talking to Amir from Mixbread on their efforts in improving re-rankers and especially focusing on Colbert. We will also be talking to, for example, Sahil from China on how to use synthetic data to fine-tune embedding models. So we have a lot of interesting stuff coming up. So subscribe and stay tuned. Otherwise, I will see you next week and have a good one.